This is the second of 3 lectures out of chapter 16, and this one is about acid-base titrations. I've noticed that it's actually reasonably common for students not to even really understand what a titration is used for. So I want to make sure you understand that first. Basically, in a titration, you have a substance, and you typically know what the substance is, but you don't know what the concentration of the substance is. And so a titration is a very precise, accurate way to determine the concentration of a substance. If you're heavy breathing, it is not me. It is one of my dogs. All right, so the material that you don't know is typically, don't know the concentration for, is typically in a beaker or Erlenmeyer flask. And then you have another substance that it reacts with in a burette, and it's delivered in a very precise way. You know exactly what the concentration of the substance in the burette is, and you can measure exactly how much of it you add. The substance with the unknown concentration is called the analyte. It's what you're analyzing. And the substance in the burette that has the known concentration is the titrant. Okay? Those two react with each other to form some type of product. And because of that, you can very accurately determine the concentration of the analyte through stoichiometry. One other ingredient, a third ingredient that's needed in a titration is some type of indicator. It's typically a color indicator that is chosen so that it changes colors right at the equivalence point. The equivalence point is when the moles of acid, for example, that you've added exactly equal the moles of the base that are in the sample. And so the bottom line is they have essentially neutralized each other, so there was no more acid nor base present in the solution. There are just the products. That's called the equivalence point. There are a ton of different acid-base indicators, and so knowing what you're titrating, remember you usually know the ingredients, you just don't know the concentrations of one of them. So knowing what you're titrating, you know what pH to expect at the equivalence point. So then you pick a color indicator that changes color at about the pH of the equivalence point. Again, there's that heavy breathing. That is Miss Gracie, my mom's dog actually. She's wanting me to throw her ball. All right, so you've done titrations enough in the lab now, so you basically know how it goes. But again, you put your analyte in an Erlenmeyer flask typically, and you deliver the titrant through a burette. And at the equivalence point, if you use phenolphthalein, that is a very common one. And it's a good one to remember what the color is. I've noticed on the lab final, a lot of times they'll ask you about that color. So it turns out that phenolphthalein is pink when it is either neutral or basic, and phenolphthalein is colorless when it's acidic. Okay, so if you have an acid in the Erlenmeyer flask that you're trying to find the concentration of, and you're adding, let's say, NaOH from the burette, when you reach, boy, that wasn't very good, when you reach the equivalence point, and it is neutral or slightly basic from a drop too much of the hydroxide, it'll turn pink. So again, at the equivalence point, you have added enough acid to completely neutralize the base that you started with. And so it is close to neutral. You'll learn as we go along that it's not always exactly pH of 7, but it's quite close to it. All right, so let's look at an example quantitatively because there are a lot of calculations involved in a titration. Let's say that we started with an analyte that 50 milliliters of it, and let's say we happen to know what the concentration of it, just for calculations point, and then it was 0.2 molar. That means we started with 10 millimoles of nitric acid. You probably have heard by now or seen me doing samples that if you multiply molarity, normally we multiply it by liters so that liters canceled, but if you multiply it by a volume in units of milliliters, you get units called millimoles, which are really commonly used in titrations, and you'll see very handy. You don't have to use millimoles. You can use a volume that has liters that will give you units of moles if you're more comfortable. So 10 millimoles of nitric acid. When would the equivalence point be if this is how many millimoles we were titrating? It would be when we had added the exact same number of millimoles of what it's reacting with, in this case a base. So let's look at an example. Let's say that we have a sample of hydrochloric acid and we don't know what its concentration is. And so we're going to titrate it to figure that out. That's something that might commonly be used. Let's say you took a sample of water from a stream or something and you wanted to know if it was acidic. Maybe there had been some illegal dumping or whatever. So you don't know the concentration of the sample of hydrochloric acid. So you know, however, that it will react with sodium hydroxide, a base, and so you fill your burette up with sodium hydroxide. That's called your titrant, and it's a very carefully known concentration of sodium hydroxide. And you drip it in drop by drop by drop until you have a color change, until you reach the equivalence point. And it took exactly 30 milliliters of sodium hydroxide to neutralize this sample with an unknown concentration of hydrochloric acid. So the question says, what is the concentration of hydrochloric acid? How do you figure that out? You're starting to do that in your labs now, and it's really important to be able to understand how to do this. They will show up on your lab and your lecture finals. So it's an important calculation to understand and be able to do. An easy way to do it is to use something that looks similar to the dilution formula, but there's a very important difference. It still has that kind of M1V1 equals M2V2. The difference if you're using it for an acid-base titration is it has these little coefficients, little a and b, in front of the M times V. And those are critical, and it's probably one of the most common mistakes made by students when doing a titration calculation. These little letters stand for the number of hydrogen ions in the molecule of acid, in one molecule of acid, or in the case of B, the number of hydroxide ions in one molecule of base. So if we had, let's say, NaOH, how many OH groups are there in one NaOH? There are 1, okay? So that means that B would equal 1. What if I had something, however, like calcium hydroxide, and I had 1 molecule of calcium hydroxide? How many OH groups would be released by 1 molecule of calcium hydroxide? 2 of them, okay? So in that case, if you were titrating with calcium hydroxide, B would equal 2 when you were doing these calculations. That's really important to remember. So here's the actual calculation for this problem. Little a for hydrochloric acid is 1. We're trying to solve for the molarity of the hydrochloric acid. Remember, it's our unknown. It is our analyte. But we did titrate 50 milliliters of it. On the base side, since we're using sodium hydroxide, little b is 1. There's only 1 hydroxide group in it. And we used 0.1 molar of NaOH, and it took 30 milliliters of that NaOH to reach the endpoint. So you really just have to be careful to match up what goes where, just kind of like in the dilution formula, and then don't forget the little a and little b. And then when you solve this reaction, of course, you get that unknown sample, the analyte, had a concentration of 0.060 molar. Here's a problem that's a little step up because the little b is not going to be 1 anymore. So we have, in this case, a base that we know, strontium hydroxide, and we know how much of it we used. We carefully measured out 20 milliliters of it. but we don't know its concentration. Okay, so it's going to be our analyte. And we know since it's a base, it's going to react with an acid, so we're going to select 0.05 molar hydrochloric acid to neutralize it and reach the equivalence point. So what is then the concentration of the sample of strontium hydroxide? The first thing you need to do is write out a balanced reaction. All right, and that's mainly so that you can look at the stoichiometry. And the stoichiometry will tell you that it takes 2 hydrochloric acids to neutralize 1 strontium hydroxide. That can be taken into account with the little coefficients, okay? So if you were to notice strontium hydroxide has 2 hydroxy groups, make sure you put a 2 in for the little b. All right, and then just put everything else in the right place. 0.05 molar hydrochloric acid. The titration required 25 milliliters to reach the equivalence point. Solve, and you get the unknown concentration of the strontium hydroxide to be 0.03 molar. If a scientist would like to generate a titration curve of showing pH versus milliliters of the titrant added, or volume of titrant, they need to measure the pH at several different points throughout a titration. And you've done that again in your lab before. And if we titrate a strong acid, like hydrochloric acid, with a strong base, like NaOH, for example, the pH starts at a very low pH, as you would expect for a strong acid. You get a very sharp jump at the equivalence point, and then it levels off at a relatively high pH. That's a typical curve for titrating a strong acid with a strong base. Another thing I'd like to point out is at the equivalence point, which is about halfway up this strong jump or sharp jump, the equivalence point of a strong acid with a strong base, the pH equals 7. That is only for titrating a strong acid and a strong base together. You have to have both of them to end up with a pH of 7 at the equivalence point. You'll see if either one of these is weak, the pH is not going to be exactly 7 at the equivalence point. This is probably common sense, kind of, but when you're used to seeing the titration curve for an acid all the time, sometimes seeing the mirror image of it can throw you off, so I just want you to look at if you were titrating a strong base instead of a strong acid. In other words, if the base were your analyte, the thing in the Erlenmeyer flask, you would start off at a high pH, obviously, because you're starting with a base in this case. Okay, and at the equivalence point, again, it's gonna be a real sharp drop this time instead of a rise. Okay, equivalence point's in the middle of that again, and then at the end you're going to have a low pH because you've neutralized all your strong base and added a little bit extra acid at the end just to make sure you've reached the equivalence point. I wanted to give you one more kind of logical look at millimoles because they're so commonly used in titrations. Again, you do not need to, but molarity, remember, is moles per liter, and so you are used to multiplying by liters and then canceling liters out. Because we deliver the titrant in milliliters from a burette, rather than having to convert from milliliters to liters, and then back to milliliters, a lot of chemists simply multiply milliliters by molarity and then work with a unit we call millimoles. It's easier, but you don't have to. All right, let's do an example. Creating a titration curve, as I said, requires that you do several pH readings throughout a titration. And so in this case, it's asking you to calculate the pH. When it says after 0 amounts of the titrant has been added, that just means before the titration begins, obviously. okay? And then at several points during the titration, after you've added 2 milliliters, 10 milliliters, 20 milliliters of base. And if you can do this type of problem, generate pH at several different levels, you are golden for the test. But this will be the most challenging type of problem you will do. So if you're tired of listening to me, take a little break and come back when you're fresh, because this takes some concentration to follow this. As I said before you add any base at all, remember that we have hydrochloric acid as our analyte, and we're dropping into it from the burette, the base, okay? Before you add any base at all you have is the hydrochloric acid, which is a strong acid. How do you calculate pH of a strong acid? You don't need an ice table, anything else. You simply use the formula pH equals minus log, okay? Our hydrochloric acid was 0.125 molar. So that will be the concentration of the hydronium ion, remember, because all of this hydrochloric acid ionizes or dissociates. So you end up with the same concentration of hydronium ion. pH minus log of 0.125, so the initial pH is 0.90. So when you're making your graph of pH versus milliliters of base added, okay, your 0 point, in other words, when you haven't added any base, the pH is going to be 0.9. Okay, so there's your first point down here. Once you have started adding any titrant, which in this case is the hydroxide, you have to use a mole table. Just like any chemical reaction, you need to work in moles to figure out how much of it has reacted and how much of it is left, and that's going to determine your pH. So let's do it for adding 2 milliliters of the sodium hydroxide. How many moles of that is it? All right, so let's first figure out the moles of HCl we had in our Erlenmeyer flask. That was our analyte. In this case, we're going to say that we knew the concentration, although normally you don't, but that's just to carry you through these calculations. So 0.125 moles of HCl to begin with times 20 milliliters. So we started with 2.5 millimoles of hydrochloric acid, which is equal to 2.50 millimoles of the hydronium ion because it all dissociates. All right, when we've added 2 milliliters of the sodium hydroxide, that means we have added 0.5 millimoles of sodium hydroxide. Sodium hydroxide and hydrochloric acid react in a 1-to-1 ratio, okay? So let's go ahead and set up our mole table, figure out how much hydrochloric acid we chewed up and how much will be left, and then we can calculate the pH. Here's our mole table. You can call these over to the left, whatever you want, before, change, or like I've been saying, during, and after the reaction. So again, as I said in the previous slide, we started with 2.5 millimoles of hydrochloric acid. We've added 0.5 millimoles of the titrant, sodium hydroxide, from the burette. And all of this is going to react because it's a strong base, so we subtract the 0.5 millimoles of sodium hydroxide, and we are left with 2 millimoles of the hydrochloric acid that have not reacted yet. Of course, all of the sodium hydroxide will be reacted. There'll be none left at the end of that reaction. And now, with knowing that we have 2 millimoles of hydrochloric acid left, we can figure out the pH. Be careful, be careful, be careful at this point. In order to get the pH, we need to go back into the concentration rather than moles for the hydronium ion. So we need to divide these moles or millimoles by the total volume of the solution. The tricky part is the total volume has changed. We started with 20 milliliters of hydrochloric acid, but we have now added 2 milliliters of the sodium hydroxide solution to titrate it. So our total volume is now 22 milliliters. Be very careful then when you figure out concentrations while you're titrating, because the volume will continue to change. So that means that our concentration of hydronium ion at this point, after adding 2 milliliters of the sodium hydroxide solution, is 0.091. If we take the minus log of that, our new pH is 1.04. That makes sense because our original pH was 0.90. We would expect the pH to be gradually rising. We're adding hydroxide, a base, so that makes total sense. Let's repeat what we just did, only instead of finding the pH after we've added 2 mils of sodium hydroxide, let's calculate the pH after adding 10 milliliters of sodium hydroxide. If you're feeling somewhat confident, I would go ahead and put this lecture on pause and try to do it yourself. All right, so after we've added 10 milliliters of sodium hydroxide, that means we have added 2.5 millimoles of sodium hydroxide. Remember that the original number of millimoles of hydrochloric acid was 2.5 millimoles. This is important to open your eyes and kind of realize what's going on. Where are we now? We're at a very special place in the titration where we've added enough hydroxide to completely neutralize the HCl that we started with. They've obliterated or neutralized each other. So the pH at this point, you don't even have to do a calculation because you have a strong base and a strong acid. The pH will be 7, always. So if you do the calculation, that's fine. It's just going to take you more time and more work. What happens if we over add the titrant? If we add 20 milliliters of sodium hydroxide, we know that after adding 10 milliliters, we were at the equivalence point. So if we added 20 milliliters, we've added too much, which is fine because that gives you the end part of your titration curve. So here's the equivalence point at the steep rise, and here's where you've added excess of your titrant. It's that flattened out part at the end. All right, but we still want to know the pH here. So you've added a total of 5 millimoles of hydroxide, but you only had 2.5 millimoles of hydrochloric acid. So how much excess of the titrant did you add? Well, we're going to go ahead and make a mole table. Even if you can do this in your head, make sure on a test that you draw it all out, show your calculations in the mole table so that you get full credit in case you make a silly math error. So, again, we've started with 2.5 millimoles of hydronium ion, or hydrochloric acid, 5 millimoles of hydroxide we've added. So hydronium ion is completely gone. We added enough hydroxide to react, and we have 2.5 millimoles of the hydroxide in excess. So the hydroxide is going to be what determines the pH since our hydronium ion is gone. So how do we determine the concentration of hydroxide? Remember that the mole table you have millimoles, not concentration. We have to divide by the total volume. How did we get 40 milliliters? Well, we started out with 20 milliliters of the original HCl, and we just added 20 milliliters of the sodium hydroxide, which granted is too much, but that's the total volume that's in that Erlenmeyer flask now. So we have to divide 2.5 millimoles of hydroxide that's in excess by 40 milliliters, which gives us a concentration of 0.0625. That is the concentration of hydroxide, which means we have a pOH of 1.2. 14 minus 1.2 gives us a pH of 12.8. Again, that makes sense. We have added too much hydroxide, so we expect that solution to have a very basic pH. So as you know from doing your lab, when you create a titration curve, remember that pH is on the y-axis. This is something you might be asked to sketch. The volume of titrant added in milliliters is on the x-axis. And you just simply plot all of the points that you have, volume versus pH, and this is the typical pH. curve. Again, whenever you titrate a strong acid and a strong base like we did, the pH at the equivalence point, which is halfway up this steep rise, is exactly 7. All right, now it gets quite a bit more complicated. If you titrate a weak acid with a strong base, okay, or conversely, we always start with an acid, don't we? But if we started with a weak base and titrated it with a strong acid, it would be similar type calculations. All right, but we're going to, for right now, work with a weak acid. The first thing I want to let you know about that is on the titration curve for a weak acid, at the equivalence point, guess what? pH is not equal to 7. Okay? And as a matter of fact, it's always somewhat greater than 7, typically around 8 or so. Okay? We'll explain why that is later on, but I just want you to get that stuck in your head for now. Because if you are shown, hint, hint, a titration curve and asked, is this a titration of, what type of acid this is titrating? You would be able to determine that by finding the pH at the equivalence point. If it's greater than 7, you would say it's titrating a weak acid. If it's exactly 7, you would say it's a titration curve for a strong acid. That's important to know. So let's go back to the question. Why is the pH not equal to 7 when you titrate a weak acid? Let me point out the key differences in doing calculations for titrating a weak acid versus a strong acid. Just to kind of remind you, when you do the calculations for a titration of a strong acid or a strong base, all it is stoichiometric calculations using a mole table and then using the formula minus log of the concentration to find pH. Pretty straightforward. So you always want to ask yourself, if you have a quiz or a test, before you start doing crazy calculations, is it a strong acid and strong base or are one of them weak? If they're both strong, just go straight to a mole table and minus log and you're done. If, however, you see that one of the things being titrated is weak, then you need to, it gets more complicated, of course. The first calculation you do will still be stoichiometry with a mole table. So you will still do that, okay? But then, instead of going straight to pH with the log minus log of H plus concentration, you will use the Henderson-Hasselbalch equation to figure out pH. And that's because when you're titrating a weak acid or a weak base, you end up with a buffer. You end up with some of the original weak acid and some of its conjugate base, okay, that is formed as you titrate, which is the definition of a buffer. So let me show you what I mean. Before we start doing the calculations, I want to prep you for the differences. So when you're working with a weak acid or a weak base for that example, or for that matter, before any base or before any titrant is added, the only thing that's present is that weak acid. How do you find the pH for a weak acid? You do not go straight to the minus log of concentration of acid. Don't forget what you learned in the last chapter. How do you find the pH of a weak acid? You make an ice table and use the equilibrium concentrations of H+. All right? So when you're dealing with a weak acid or a weak base and titration calculations in the very beginning, before you add any titrant, make an ice table. You might want to start taking notes at each stage of the titration of a weak acid so that at the end you have a summary and your head isn't just spinning around. All right, so before the titration begins, you're simply dealing with a weak acid dissociating and trying to determine how much of it is dissociated. So once you begin the titration, what you end up with is the original weak acid, and then assuming you haven't reached the equivalence point, you have also generated some of the conjugate base. So what do you have when you have both a weak acid and its conjugate base? You have a buffer. So really, while you're titrating a weak acid or weak base, you're just generating different concentrations of a buffer, which means you will use the Henderson-Hasselbalch equation to calculate pH. Okay, so we have two steps in the titration we've talked about. One at the very beginning and another as we add titrant, but we're not at the equivalence point yet. Let's look at those two calculations. We're going to titrate acetic acid, and if you haven't memorized your weak acids and bases, you definitely need to do it now. Notice they give you a Ka. That should be a real flag to you anytime you're given a Ka that you probably are going to need to do an ice table. And we're titrating with a strong base. Doesn't matter though, we still have a weak acid, which means we're in for the more complicated calculations. Wants to know the pH before the titration has begun. So there is no NaOH at this point. Don't be doing a mole table. All we have are the weak acid in water and showing that it dissociates. Okay? Set up your ice table like you learned in the last chapter. No tricks here. Original concentration of the weak acid. In the beginning, assume none of the dissociated form. Use your X's. Okay, this is a 1-to-1-to-1 stoichiometry. And go ahead and plug into your Ka value. So that would be x squared over 0.10 minus x. That's this. Okay, and that equals the Ka value, which is given 1.8 times 10 to the minus 5. That is a small enough Ka value that we're going to go ahead and neglect x. We're going to show that we're doing it though. And you will find that when you solve for pH, you get the initial pH of this weak acid at 2.87. During the titration, once you've started to add the base as the titrant, that's when you have two calculations you're going to have to do. As always, for any type of titration, you need to set a mole table up. Okay? Every titration will have that. What's different about titrating a weak acid is after you use the mole table to determine how much is reacted and how much is left, then you still need to use the Henderson-Hasselbalch equation rather than just minus log of concentration to find pH. All right, so here we go. When we've added 10 milliliters of the titrant, sodium hydroxide, what is our pH? Okay, so here's the mole table first. Okay, mole table. Whoops, not null, mole table. All right, so before the reaction, you have to read the problem to begin with. It told us, or we found, that we had 5 millimoles of acetic acid. We have added 1 millimole of hydroxide. How do I know that? Because 10 milliliters of hydroxide times its concentration, 0.10 mole per liter, tells me that I've added 1 millimole of hydroxide. All of that's going to react, which leaves us with 4 millimoles of the original acetic acid. Of course, all the hydroxide is going to be gone. It's been chewed up by the acetic acid. And because all the stoichiometry is 1-to-1-to-1, we have formed the same amount of acetate, the conjugate base of acetic acid. Now you have your base and acid concentrations, which you will now plug into the Henderson-Hasselbalch. So here we go with that. Here's the Henderson-Hasselbalch equation. We were given the Ka, so there's that, minus log of the Ka. And here is the concentration or the mole, either one is fine, of the base on the numerator and the acid in the denominator. By the way, I notice I'm working with a bunch of students that mixing, putting the acid and base in the right places is an incredibly common mistake. So look at your two species and make sure you understand how to determine what the acid and the base is. If there's a negative charge, that will always be the base. Okay, the base will also be missing a hydrogen atom. Okay, and the acid is always going to have an acidic hydrogen, typically neutral. So anyway, be very careful because you'll get the wrong answer if you invert those. So the pH at this point, after we've added some sodium hydroxide, is higher. So instead of 2 something, it's 4 something, which makes sense. Now, at the equivalence point, the pH is not equal to 7. That's what we didn't even have to do a calculation when we titrate a strong acid with a strong base, because in that case, the pH was 7, and we knew it. If you are titrating a weak acid, remember the pH will be slightly higher than 7, 8 something typically. So you have to do a calculation at the equivalence point is the bottom line, unfortunately. So why? What's making the pH greater than 7 at the equivalence point when we've titrated a weak acid? It's because what's present at the equivalence point? The original reactants are gone, okay, 0. They've all neutralized each other. What do we have present? We have this guy. What is that? That is the conjugate base. It's actually a weak base. It's going to make the solution a little bit basic, that conjugate base that's left at the end, enough to make the pH around 8. So in order to know the exact pH, we have to figure out how much of this we have and how strong it is. So basically, when you reach the equivalence point, what you do is you identify the conjugate base that's formed, in this case the acetate ion, and you simply write the chemical reaction representing Kb. In other words, like any weak base, it can react with water. What does it do? It reforms the original weak acid with some hydroxide left over. Remember this, what bases do, they just snatch a hydrogen ion from water. Okay, that's all we've done. But because of that, because it's formed hydroxide, it's going to make a basic solution. So how do you find the pH of a weak base? You set up an ice table and you find the pH from the ice table. Remember, since it's a base, though, you need to use Kb. Do not use Ka. If you're given Ka, you need to find Kb. Remember how to do that? It's Kw over Ka. And Kw is 1 times 10 to the minus 14. So let's walk through that calculation. All right, so here we go. I've written the reaction. This is at the equivalence point when all we have present in solution is that weak conjugate base. Here's the reaction it undergoes with water. This is why it's making the solution have a pH that's basic, a little bit more than 7. What is our initial concentration of the weak base? Be careful. It is 0.005 moles, and that is the original number of moles of the acetic acid, the weak acid that we started with, okay, just as you would expect, because for every 1 acetic acid we can only make 1 acetate. However, as with any titration, what has changed is the total volume. We started with 50 milliliters or 0.05 liters of the original acetic acid, but then we've added another 50 milliliters during the titration. So the total volume has changed, has moved from 50 milliliters to 100 milliliters. So be careful of that in a titration. Just like any ice table, 0 product to begin with, or most ice tables I should say, a certain amount of this acetate ion is going to dissociate. We represent that with X. And so our final equilibrium concentration of all of the species are here. We can plug those into our expression for Kb. That will give us the concentration of hydroxide, since it's a base, not the concentration of hydronium. And from that, and a couple more calculations, we'll be able to determine pH. So as I mentioned before, we were given Ka in this problem, 1.8 times 10 to the minus 5. we don't need Ka at the equivalence point. At the equivalence point, it's all been converted to the base, so we need Kb, which is simply Kw divided by Ka. And so the Kb we need to use for our ice table is 5.5 times 10 to the minus 10. Very, very small. That's good news because that means that it's safe to neglect x. So we originally had down in the denominator 0.050 minus x. That x is going to get neglected. Yay! So it's easier to solve. X, which if you go back to the ice table, represents the concentration of OH at equilibrium. So now we can finally find POH. pH then is 14 minus POH, which is 8.72. That is the pH at the equivalence point. And as you can see, it is greater than 7, as it should be for a weak acid. Shoot. So now, remember there's one more stage in a titration, and that is it when you add excess OH, excess of the titrant, which is typical in a titration. What will the pH be at this point? Well, you'll be happy to hear you work this problem exactly like you do when you add excess titrant for a strong acid, strong base. No difference. So to give you the summary, this is a typical titration curve for titrating a weak acid. Make sure that you can differentiate this titration curve versus one for titrating a strong acid. The key difference is that at the equivalence point, and again, that's about halfway up this steep jump, halfway is the equivalence point, carry that over to the y-axis, that tells you the pH at the equivalence point. For a weak acid will always be greater than 7, and that's how you determine that the graph is for a weak acid titration. Here's a summary slide that you may want to jot down because there are seemingly so many different steps in calculations for titrating a weak acid. And so just to quickly summarize, and again you may want to jot this down, the initial pH, and again this is only for a weak acid, is determined using the Ka of the weak acid and an ice table. Okay. During the titration, you treat it as a buffer, which means you first do a mole table and then you use the Henderson-Hasselbalch equation. Okay, that's during the titration. So that's one type of calculation. Here's the second type of calculation. The third different type of calculation is at the equivalence point. At the equivalence point, all you have left is the conjugate base. So again, you set up an ice table, but this time for the conjugate base and using Kb. At the end, the pH after the equivalence point, so that means when you've added excess titrant, is simply using minus log concentration of OH that is in excess, the excess OH that you've added. Okay, that will give you POH, just like we did when we titrated a strong acid, if you need to go back and refer to that. All right, so again, wait till you're fresh and you wait till you try this on your own. Go back and write down that summary slide if you didn't. You can refer back to how I did these, but you really need to try this on your own. So let me get you set up for the problem. This would be a typical problem in your test. You will see something like this on your test, and the only way to be able to do that is struggle through on your own. So this question, again, wants you to calculate pH at a number of different points. The first thing you want to notice is formic acid. That is not one of the strong ones, so that is a weak acid, which means, okay, ice tables, Ka, Kb, etc. Okay, here's the Ka value, which you will need. You're titrating with sodium hydroxide, no surprise there. And it wants you to calculate the pH at 1, 2, 3, 4 different levels of base. So here we go. What do you do at the beginning of the titration? At 0. That means you haven't added any base. You don't even need this reaction in the beginning. What do you need in the beginning? All you have is the original acid, which is formic acid. What is it going to do in water? There's no base added, so don't be writing a reaction with hydroxide yet. It's going to be in equilibrium with its partially ionized conjugate base and a little bit of hydronium ion. Okay? So just like you did in chapter 15, you set up the ice table with formic acid, typical of any weak acid, and you solve for X, which will represent the concentration of the hydronium ion. Okay? You're going to be using Ka, and then you can find pH. So go ahead and give it a shot for 0 level. Did your ice table for adding 0 milliliters of sodium hydroxide look like this? I hope so. Ka is just on the borderline of being negligible, but it's probably okay to neglect the X or Y here. Y equals, remember, concentration of hydronium. That's how you're going to get your pH. When you solve for this, you should have gotten hydronium ion concentration, 9.5 times 10 to the minus 3. And then if you take the minus log of that, you will get the initial pH before the titration has begun. And that pH would be 2.02. That is the initial pH at 0 milliliters of NaOH added. All right, here we go. Now when you have added some of the hydroxide, and it's a weak acid to begin with, remember that there are 2 calculations. The first one, as always, regardless of the type of acid, is a mole table to figure out how much is reacted and how much is left over. But in this case, since it's a weak acid, you will then be using the Henderson-Hasselbalch equation to figure out pH. So go ahead and try it on your own. Put this on pause, and we'll see how you've done. Check and see that you set up your mole table first. Remember, even if you're able to do this mole calculations in your head, on a test you need to show your work. Hopefully you got this from the mole table, that you have 5 millimoles of the original formic acid left, and you have formed 5 millimoles of the conjugate base. In other words, you were at the 1 halfway point. So listen really careful at this point, because this can save you a lot of work. The halfway point is magic when you titrate a weak acid, because look what happens. You don't even have to do a calculation if you realize it's the halfway point. At the halfway point, when you have half of the original acid left and you have formed half of the conjugate base that you're going to, this ratio in the Henderson-Hasselbalch equation goes to 1. And what is the log of 1? It is 0. So what does that mean? That means at the halfway point, pH equals pKa. So you don't have to do any calculations at the halfway point. All you have to do is figure out what pKa is. Remember what that is? It's minus log of the Ka value, which is given to you. So at this point, after 10 milliliters, I think a base was added, the pH is 3.74 instead of 2 something. So it's going up as you would expect because you're adding base. All right, so here we go again. After we've added 20 milliliters of the hydroxide, again, please try to do this on your own. So turn me off and then turn it back on. So at this point, when you've added 20 milliliters of the base, since it was 0.5 molar, when you multiply those by each other, you have added 10 millimoles of OH. If you remember the last mole table we made, we started with 10 millimoles of the acetic acid. So where are we at now? We are at the equivalence point. When you've added enough base to completely neutralize the original acid, that is the equivalence point. That's important because that tells you how to do your calculation. So you no longer have to do, if you recognize you're at the equivalence point, you don't have to do a mole table. You don't have to use Henderson-Hasselbalch. In fact, you can't use Henderson-Hasselbalch. You have to realize you're at the equivalence point, and what do you have present in the solution at the equivalence point? All you have is the conjugate base of the original acid. The acid has been completely obliterated or neutralized by the titrant, and this is all you have left. So if you can solve this, go ahead and go for it. If not, I'll remind you how to do it. This is a weak base. The conjugate base of a weak acid is also a weak base. So you need Kb. You need to set up an ice table and figure out initially concentration of hydroxide that it's made, and through that then the pH. So we are going to need the concentration of that conjugate base. We know that we've made 10 millimoles of it. That was the original amount of the weak acid we started with. We also know that the total volume of the solution has increased because we have added titrant. And so the concentration of the conjugate base is 0.250 molar. Let's go ahead and set up our ice table now. Here is the conjugate base. It reacts as any weak base in water in an equilibrium, and it forms some of the original weak acid back. We set up our ice table like we always do, the original concentration. We have to figure out Kb. It is 5.6 times 10 to the minus 11. That is very, very small, which I personally am always happy to see because it means we can neglect this x or y. Plugging those values in, and solving for y, which equals the hydroxide concentration, we get 3.7 times 10 to the minus 6 molar. Taking the minus log of that, we get that the pOH is 5.3. Don't forget to switch it to pH, which should be 14 minus 5.543. pH is 8.57 at the equivalence point. That's what you would expect at the equivalence point for a weak acid. It is above 7. Okay, now, when we've added excess base, so we know that it took 20 milliliters of hydroxide to reach the equivalence point. So anything over 20 milliliters is going to be excess. Here's a mole table to figure out the excess. So of course all the original weak acetic acid is gone. We only needed 10 milliliters of the 10 millimoles of the hydroxide to neutralize the acetic acid. And since we've added 15 milliliters, I think I may have said 20 on the other page. Sorry if I did. Anyway, you have 5 millimoles of the hydroxide left over or in excess, and that's going to be the sole determiner of the pH. So really all we need to do now is figure out the concentration of that excess hydroxide. And that we do that by dividing by the total volume. We started with 20 milliliters of the acetic acid solution. And we have added, whoopsie daisy, we have added another 30 milliliters of the titrant, the sodium hydroxide solution. And so the concentration of hydroxide, excess hydroxide we have is 0.1 molar. We can get the pH from that. So we have to get pOH first, of course, minus log of the hydroxide concentration. And that gives us a pOH of 1. pH then is 14 minus that. So our pH, when we've added excess hydroxide, is 13, which is what you would expect. So here's a typical titration curve for titrating a weak acid. A couple things key to remember. The equivalence point, the pH is going to be greater than 7. And remember that this is considered a buffer zone in this whole region before you reach the equivalence point and at the halfway point. So let's see, the equivalence point happened at 20 mils, so the halfway point would be 10 mils. And so at this halfway point, the pH equals pKa. All right. I'm not going to go through this one in as much detail, but you need lots of practice with this. A couple years ago, almost my entire exam was titrations, because I figured that if somebody could do a titration, they could basically do everything we've learned in these two chapters. They could calculate the pH of a weak acid or a weak base. They could calculate the pH of a buffer. And so I gave that thinking that would be the best type of exam, and it threw a lot of people off. So I will not do that again, but I will definitely ask you titration questions. So real good to do this for practice. So try to do it on your own. I'm going to go ahead, I'm not going to work them out in this lecture, but here are the answers for you. And I would strongly suggest that you try to work these out, going back to the slides where I've worked out a problem if you need to. I like to keep showing you titration curves for a base, just so that you're familiar with what they look like. Remember that any substance that has a nitrogen atom in it, or is called an amine, that's what they're called by organic chemists. It's supposed to be an A. If they're neutral, are basic. Okay, and that's because of that lone pair of electrons there like to snatch protons or hydrogen ions. Okay, so but when you're titrating a base, remember that your initial pH is always going to be high, and that your ending pH is always going to be low. If it is a weak base, as this is, kind of a similar situation at the equivalence point. At the equivalence point, look at what the pH is if you're titrating a weak base. The pH is less than 7 if you're titrating a weak base. Remember that if you're titrating a weak acid, pH is greater than 7 at the equivalence point. So remember, that's a little tidbit you're going to need to know for the test. This is going to seem a little off task at this point, but there are a couple of mastering chemistry questions about this, and I think you should just be familiar with polyprotic acids. I'm not going to go into a lot of depth. Poly means many, right? Or more than one anyway. So a polyprotic acid would be anything with more than one acidic hydrogen. Now it's just not any hydrogen, it's an acidic hydrogen. H2SO4, H3PO4, okay, those are polyprotic acids. That means simply that when you put them in water, they can potentially donate 2 or more protons or hydrogen atoms. So this is often called Ka1, this equilibrium expression, and that means that this polyprotic acid has donated only one of its acidic hydrogens. When it donates a second one, it would be called Ka2. So that means that you take the conjugate base from step 1 when it's donated one proton and make it donate a second one. All right? So be familiar with this, how to write that out for that step 1, step 2 for a polyprotic acid. Ka1 and Ka2 are quite different, as you would expect. Ka1 is always quite a bit larger than Ka2 because it's a lot easier to donate the first proton. Okay? It takes a lot more energy to donate the second proton because you already have a negative charge. Substances aren't likely to want to take on a double negative charge, which is typically what happens when it donates its second proton. Be familiar, know how to write out the Ka1 and Ka2 equilibrium expressions. Know this whole page. That's about the extent of what I expect you to know for polyprotics. I lied a little bit. If you look at a titration curve for a polyprotic acid, it will have two two equivalence points, two sharp rises. One is for loss of the first proton, okay? And the second is for loss of the second proton, okay? So obviously, a few things you can get out of this slide. The first proton, okay, is going to be have an equivalence point pH different than the second one. But the bottom line is what I want you to know here is if you see a titration curve with more than one hump, it means it's a polyprotic acid or base. It turns out that dealing with most polyprotic acids is a lot simpler than you would think because there's a rule of thumb that says if Ka1, the first ionization or equilibrium, is quite a bit larger than the second loss of the hydrogen atom, if they're different by a factor of 1,000 or more, then you can actually ignore loss of the second proton. What that means is if this difference is 1,000 or more, 10 to the third or larger, then you can treat it simply like a monoprotic acid, okay, and you can just ignore the second ionization constant. That is it for Lecture 2 out of Chapter 16.